So first of all, I would like to thank the organizer for inviting me to this conference. So today I am going to talk about Weyl Algebra and Hyperabolic plane. As you can see, the title. It is still an ongoing work with Professor K.B. Sinha. And first of all, I would like to say something about what is the relation with non-commutative geometry in this talk actually. So what my perspective about non-commutative geometry is like purely mathematically you have to have some kind of algebra instead of space which will act like philosophically would like to think that as space, and if you want to study various kind of property of that quote unquote space, you have to have some kind of probe depending on your choice, maybe a first order differential operator or maybe a second order operator depending on your choice, like Alan Kohn does it with Dirac operator, which is a really first order differential operator. And it turns out that that first order differential operator, which is called the Dirac operator, is more suitable to study the topological property and geometrical property. And what I am going to talk today is it's more with the philosophy of Weyl, where we have a second order differential operator like a Laplacian, and by studying the growth of its spectrum and all, you can get some information about the geometry of the underlying space. My talk will be more on that line. So this is with that, let me start. So I will start with some already known thing, like what do you mean by Weyl algebra on plane before going to hyperbolic plane. It is actually, it was known, it was done, and depending on that work actually we will start whatever we are doing. So what is a Weyl algebra on real line? So first of all, what are the Weyl relations? So the Weyl relations are just they are the canonical commutation relation, but they are in the Weyl form, meaning that we are not really looking at the what physicists call position and multiplication, or position and momentum, sorry, which is multiplication and differentiation operator. Rather than looking at the commutation relation between them, what we do, we look at the commutation relation between the one parameter group generated by that two self-adjoint operators represented on L2 of R. And you can see those one parameter groups are given by ut acting on that function f, given by it is very well known. And the canonical commutation relation in the Weyl form is that ut vs equal to e power its vs ut. And this relation actually appeared in various guys in this conference already, like in case of Weyl plane and non-commutative truss, basically same kind of commutation relation. And then for Ts in R2, let us define this unit. This is actually this article really to get some nice formula. But what are important is the definition of these two one parameter groups. One is for the multiplication and one is for the differentiation. So what are the Weyl algebra? Now you take any function or in two variables, take any suitable class, let's say Schwarz class function in two variables, and let us define this operator on B of L to R. What's the definition of this operator? This is integral over R2, take the Fourier transform in two variables and plug in that unitary operator I just defined. And it turns out that this is a bounded operator represented on L to R. And you can really prove these things, like it has a bounded, and the operator norm is bounded by the L1 norm of the phi r, because this is Schwarz class function, so you have good L1 norm and all. And you can prove that indeed this, if you define by the algebra by A infinity, Weyl algebra by A infinity, such that your algebra is collection of all such B phi's corresponding to this class, it is indeed an algebra. You can prove that B phi and B psi, if you compose that, that will be B of phi star psi. This again actually appeared today itself, I think in the morning, that it is some kind of twisted convolution. You have your usual convolution between two Schwarz class functions, but it gets twisted by this factor, and that is why actually this is actually a non-commutative algebra, and the star structure is given by that. So in that way you can prove that it is a star algebra, star subalgebra of B of L to R. The thing is that this star algebra is no longer unital. If you the reason is clear. I mean, in order to have the identity, your phi should be replaced by the one function, but one function doesn't belong to is not a Schwarz class function on whole of R2. So this is a star subalgebra, and it turns out that the sister completion actually will generate compact operators, still not unital. The compact operators on B of L to R, but if you take the Hornemann closure, it will generate the whole of B of L to R. So it should be B of L to R, I think. It is not R2. So, but we are not taking any sister completion or Hornemann completion, as we have already seen that often to study the geometric properties, it's enough to look at the star algebra itself rather than taking any sister or Hornemann closure. So, as it is not unital algebra, so in principle we are looking at non-compact space, because if you are really talking about compact topological space, we should look at unital algebras, but this is actually non-unital algebra. And one can show that in this algebra there is a unique trace given by the first Fourier coefficient or the integral of the function on R2, and this GNS Hilbert space, actually the dimension of this GNS Hilbert space gets actually down, and it is not really L2 of R. It actually turns out that it is L2 of R2, and on that Hilbert space, this algebra also has a representation. You can have a representation by left multiplication. You take any vector B psi, you left multiply by T multiply by B phi, that is another representation. Okay, so that was actually already known that we can have this kind of Weyl algebra on plane, and it can be generalized. I have only talked about Weyl algebra on R. It can be generalized on any Rn, and you start with Rn, then you take any function from R to N and generate the corresponding Weyl algebra, which will be represented a priori. The defining representation space will be L to Rn, but it has another representation space also. Like if you go to the GNS space of the star algebra, you can represent it also on that algebra. So we will be mostly talking about this representation when we want to talk about some geometrical property of the space. So what is it? Now what we are going to do? We are going to extend the concept of this Weyl algebra on plane to Weyl algebra on hyperbolic plane. So what is hyperbolic plane? Quickly, we will do it for only two-dimensional hyperbolic plane. So we will not get to general n-dimensional hyperbolic space. So what is a hyperbolic space? We will stick with upper half plane model. What is the upper half plane model? It is given as a set. It is just x, y. X is on the whole real line and y is actually upper half. Sorry, the positive real line. So that H2 is really upper half plane. That's why it is called the upper half plane model. And to study the geometry, you have a metric actually, and the metric is given by on diagonal 1 by y square, 1 by y square, and off diagonal 0, 0. And with respect to this metric, the hyperbolic volume measure is given by dx dy by y square. These things are well known. But the thing is that when we started to construct Weyl algebra, it was very clear that how did we construct Weyl algebra on plane? We took the multiplication operator, and via Fourier transform we can go to the differentiation operator, and we sort of form function of those two variables. That is roughly the Weyl algebra in mathematical way. But if we have upper half plane, we have position operators to multiplication operator. What should replace the notion of the differentiation operators? Because we don't have any. We'll get into trouble because there is a problem with the Fourier transform there. So, but luckily, what we have a global change of coordinates like x by y and log y, and we can map the whole of H2 into R2 by that change of coordinate. And it turns out that if we use this change of coordinate, then we can have actually a unitary map which maps this Hilbert space L2 of H2 with that hyperbolic volume measure to L2 R2 with Lebesgue measure. That's a unitary map between two Hilbert spaces. So what we have done, we have used actually that map to construct our position and sort of momentum operator and then study the Weyl algebra. But what we have in mind that we want to study some geometric property of that algebra. So how do we study that? For that we have to look at some operator which can act as a probe to study some geometric quantity. So for that, what we have done is that we have actually defined some analog of Laplacian on that algebra. For that, let us recall what is the classical Laplace-Beltrami operator in hyperbolic plane. So it is very well known that this is given by this thing. Maybe there is a minus depending on the convention. It is y square del x square plus del del square. But if we change the coordinate, remember I have just talked about the change of coordinates. If we do this change of coordinate, say let us call these coordinates as tau 1 and tau 2. With this new coordinate, this Laplacian will look like this thing. By delta bar, we mean these vector fields del del tau 1 and del del tau 2, and the metric will look like this in the coordinate. That one can easily see. So that will be our guide to construct like a Laplacian and Weyl algebra. What was done previously to study Weyl algebra on plane, after the plane gets doubled, like from one dimension position to position and moment operator, it gets double. And if you define a Laplacian, if you restrict to one corner of that is actually a commutative algebra. That corner we want to recover the classical Laplacian, Euclidean Laplacian. So that was our guide. So we want to do similar thing here. Whatever we will define as a Laplacian or a Linglardian, whatever, but it should give on proper subalgebras or subcomponent planes, rather I should say, this Laplace-Beltrami operator. That has been sort of guide to define such operator. Okay. Now, then what is the Weyl algebra on hyperbolic plane? So maybe we can actually, what happens that once you have this unitary operator, like this unitary operator which maps L to H to d mu to L to R2, you can pull back the whole information of R2 to actually this Hilbert space, like L to H to d mu. More precisely, you have these two operators U1 and U2. They will act as sort of multiplication. U1 is actually generator of the differentiation operator, and U2 also that. Actually, V1 and V2 are generator of the multiplication operator. One multiplication operator is actually multiplication by x by y, the new coordinate. Another is multiplication of log by y. That is why it is appearing as y power is2. One can check, and they are the conjugate sort of one parameter groups, meaning that via that unitary you get U2 from V2 and U1 from V1. And one can see that the Weyl commutation relation is actually same what was there in case of, actually if you take R2 not R, if you start from R2, then whatever Weyl commutation relation, you get the same Weyl commutation relation. So similarly, you can define for this T bar and S bar actually a vector. T is T1, T2 and S is S1, S2. So if you take a vector from R4, any Schwarzschild function phi on R4, then you can define, again using the same machinery, you can define this, and this will be represented on B of L2 H2 or R2, depending on which representation you are really talking about. You can go from one representation to another representation by using that unitary I already discussed. Nothing changes really. As far as the algebraic property is concerned, nothing changes. The algebraic property is the same as if you had Weyl algebra on R2, say. So in this direction, yeah, the algebraic properties actually remain same, because the commutation relation actually don't change here. If you look at it closely, the commutation relations don't change. That is why the algebraic properties actually don't change. And as I already mentioned, this will again be a non-unital, non-commutative star subalgebra. And again, if you take the representation on A infinity, on the space A, the completion Hilbert space of A infinity with the unit trace, which will be the, as Hilbert space, which will be actually isomorphic to L to R4, then you have a representation of A infinity L to R4 also. So we will stick to that representation. Now let us talk about component planes, because what we have done after defining the Laplacian on the whole sort of 4-dimensional plane, we have chosen a suitable subplane which looks like Weyl algebra on 2 variables, and we tried to actually study some geometric properties of that. For that we will just talk about component planes of the Weyl algebra. So if you remember that phi was Schwarzschild function of 4 variables, and if we restrict that phi to be a function of only suitable 2 variables, say u1, u2 or u1, v1 or u2, v2, you will get the corresponding planes. So the definition will be given by that, one can check that, and these will be plane, but they won't be really sub-algebra of the whole Weyl algebra, because if it doesn't depend on 2 coordinates, then on the 2 coordinates you are putting only 1, and it won't be Schwarzschild in the all 4 variables. Maybe it is a Schwarzschild in 2 variables, but in the rest of the 2 variables it is no longer Schwarzschild. So they won't be sub-algebra, but still you can, look at them as some sort of component place, some 2-dimensional subplane sitting inside the whole plane. So these are the component planes. And in order to define some kind of operator, so what we will do is that we have to find some derivation, and some combination of the derivation will give rise to that operator. So what are the derivations? What kind of derivation do we have on Weyl algebra? So these derivations are called, we would like to call it canonical derivation. These are known actually on Weyl algebra. If you take, since phi is a function of 4 variables, so we already have 4 kind of direction where you can differentiate the function on these 4 directions, and they will generate derivation that one can check, and it was there, it's already there. What we have done, we have found another derivation actually, which will sort of be non-canonical, and it comes from a symmetry of the algebra. One can show that SP4 is actually part of the full symmetric group of the algebra. We have not found the full symmetric group yet, but symplectic group is a part of the larger symmetric group actually, and corresponding to this 1 parameter subgroup of SP4 given by this thing, actually one can define derivation actually, the generator of the 1 parameter group of automorphism, that this derivation is the generator of the 1 parameter automorphism group, and one can compute that. This is given by B phi. If you apply R on B phi, then this is the formula of the derivation. This is a non-canonical derivation. This was actually not observed earlier. I won't say not observed earlier, but we have got this derivation. Now once we have some some supply of derivation, how to define a suitable Laplacian which can sort of capture some of the geometrical properties, if at all. So for that we have defined what we have called actually metric matrix. What is a metric matrix? First of all, the metric matrix, if you think classically even, the metric of the whatever your geometrical structure is actually encoded in a matrix, and we have actually imitated that thing, that first of all you have the space of derivation, and our definition actually depends on choice of derivation. It is really depend on, you can say that it depends on sort of choice of basis of your whatever your space of derivation. So we already have, suppose that we have chosen a set of canonical derivation, n derivation. It is general definition. I am not talking about 2 or 4 dimension. We need only 2 or 4 dimension, but still. So if you have a matrix which is in Mn LM, meaning that all the entries are actually linear maps on the star algebra, and we have a n cross n matrix, all the entries coming from actually linear maps on the star algebra, and such that all the entries are star preserving linear maps. It has a star structure, so it makes sense to talk about star preserving linear maps, and it can be, furthermore, it can be written as sigma t sigma for some matrix such that this thing actually is again in this space. I will just explain what is meant by this. This thing is actually analog of, you can say that, positivity. Like you have a factorization of the matrix, you can write it like that, so that sort of positivity. So what is meant by this notation? This notation will mean that suppose you have this choice of canonical derivation, and any ijth entry of that matrix is given by again a linear map, which will denote by Cij. Then the jth entry is summation Cjk del k, where this is actually composition. Remember, this is a linear map. The derivation is a linear map from the star algebra to the algebra itself, and this thing is also a linear map. So it makes sense to talk about composition of these two maps, and by that notation we actually mean this. And we have put only one restriction. After it will be on LA, direct sum LA, but what we demand is that it should land in the space of derivations also. It need not be, after it need not be, but such a choice will call them a metric matrix. An example will be given by, like we have already discussed, the metric on the changed coordinate in hyperbolic plane given by 1 by tau square or minus tau 1 tau 1 1, and the factorization matrix one can easily see that tau 1 minus 1 1 0 will be a first factorization matrix, and tau 1 you can look at as linear map on the star algebra, on the function algebra on the hyperbolic plane. So once we have that metric matrix, what will be our Lindbladian? So suppose that we have n canonical star preserving derivation, that choice is fixed, and then a Laplacian or a Lindbladian will be given by this notation. This notation is again, as I described earlier, you should take it as composition of maps, and where this M is actually a real metric matrix. And you can see that if you choose the derivation del tau 1 and del tau 2 coming from vector fields of the classical hyperbolic plane, and with this real metric matrix, actually this indeed turns out to be a hyperbolic Laplacian, classical hyperbolic Laplacian. So in our Weyl algebra, we want to define such a Lindbladian. How to define? Suppose that we have two star preserving linear maps given by gamma 1 b phi is b of u1 phi, 1 is the first coordinate, and eta 1 is given by b of u1 phi. Then one such choice of a metric matrix is given by this thing. One can check that this is a choice of metric matrix, and it will produce two actually hyperbolic Laplacian on these two corners. This will correspond to u1 u2 plane, and this will correspond to v1 v2 plane. Both of them are actually commutative. One can see that they are commutative because they will be generated by u1 t1 and u2 t2, and this corner will be generated by v1 t1 and v1 t2 and v2 t2, and they are actually commutative. So on this corner we will have two commutative planes and two hyperbolic Laplacian. But we want to take this as Laplacian. We want to mix things so that we have something on the non-commutative subplanes rather. So to get something non-trivial on the non-commuting component planes, what we have been able to define a metric matrix. It is given by, again, this matrix. This is a 4 by 4 matrix, as we have already seen that we need a 4 by 4 matrix. The entries are comprised of 4 star preserving 16 star preserving linear maps, gamma 1 square, gamma 1 and eta 1 I have just defined, these two maps. And the factorization matrix, actually we have back calculated, we have taken a factorization matrix and we squared it to get such a metric matrix. And by using this metric matrix and the canonical 4 derivations as I have already spoken, that delta 1, delta 2, delta 3, delta 4, let us remind it. This canonical 4 derivation, delta 1, delta 2, delta 3, delta 4, indeed that turns out to be a Laplacian, because if you take the factorization matrix and apply on this column vector, it is actually mapped to this thing, and this all the 4 entries are actually derivation. If you look at it carefully, that gamma 1 delta 1 minus eta 1 delta 3, this is nothing but the derivation are already discussed. The non-canonical derivation I just discussed, this derivation, and rest of them are actually canonical derivations. So these are again derivations, these are all the 4 entries. So in our sense, this will give rise to a Lindbladian. Now if we want, we will just write the Lindbladian in this form, then it will give rise to a Lindbladian. And the thing is that if we just compute it, that this Lindbladian actually given by this, and this actually satisfies the second order cosine condition, meaning that if you hit it L of AB minus A LB minus LAB, it will be some combination of derivations. So as I have already said that we will be interested in studying the component planes. Let us see how this Lindbladian, when restricted to component, how this Lindbladian actually looks like. So we have 4 component planes. If you restrict that Lindbladian to this commutative component plane, it will be given by this object, and you can see that this is actually first order perturbation of the classical hyperbolic Laplacian on the plane U1 U2 commutative plane. And this piece actually is again a 2-dimensional Weyl algebra, this subplane, and on that 2-dimensional Weyl algebra, the Lindbladian actually restricts to r square plus delta 1 square plus delta 3 square, and this commutative plane, it is restricted to that, and this is another piece of Weyl algebra, 2-dimensional, and there the Lindbladian actually restricted to delta 2 square plus delta 4 square. And this Lindbladian actually was studied in the same paper where the Lindbladian, when the Weyl algebra on n plane was actually studied. This Lindbladian, the spectral analysis of this Lindbladian was done. I will go to let us keep stochastic process. We want to talk about stochastic process. Let us go to the geometry of the component plane P U1 V1. This is a 2-dimensional Weyl algebra sitting inside that 4-dimensional thing, and we will study some geometric property. You have been able to study some geometric property of this subplane, so to say. So for that, to study any geometric property, as we know that we have to represent the operator in some Hilbert space to study its spectral property. So what is the Hilbert space? We want to represent the restricted Lindbladian. It is L2R2, and in L2R2 we can define 3 actually quadratic forms given by the inner product of those derivations, if you can, if you remember, and these quadratic forms actually will generate the operators A, B, C, delta 1 square, delta 3 square, and R square, and the formal sum will take to be L. This is a self-adjoint operator on L2R2. But it is formally, it looks like L U1 V1. If we go back to this slide, it formally looks like this, but on nice functions. We have some domain issues because it is self-adjoint operator. It only formally exists with L U1 V1 on some suitable class. Now, I mean, like what was previously done, if we want to get some information about volume and dimension, so what we want to do, we want to study some asymptotic behavior of the trace of the operator B for e power tl, because it is self-adjoint operator. We can do that. We want to study the asymptotic behavior of this operator acting on L2R2 for small t. First of all, we have to prove that this is actually a traceless, so that it makes sense to study the behavior of the trace of the operator. And like in the classical case, the dimension is by studying the behavior of asymptotic behavior of the trace, we will get both dimension and volume at one go. This is the hope. And for that, the problem with studying the trace of this operator is that we have sort of 3 operators, delta 1, delta 3 and R. We can go to the Fourier space, but delta 1 and delta 3 gets diagonalized in the Fourier space, but this operator actually doesn't get diagonalized. That was the problem, sort of technical problem to study the behavior of the trace. For that, what we have done, we have gone to actually, we have used some probability technique, like let omega 1, omega 2, omega 1, omega 3 and omega 2 three standard independent standard Brownian motions, and by using Joardar-Kato product formula, one can show that with this notation, let E k f of this random variable, this is integral with respect to the Wiener measure on the path space. One can show that if we apply E1, E2, E3 to this object, it is given by just you take break this interval 0 to t in some partition, and you take directed product of this thing. One can show that as a simple calculation, and using Joardar-Kato product formula, e power TL will be given by the strong limit of this thing. The thing is that we have actually commutation relation between these three one parameter group, which are actually generated by the derivations. Let us, oh sorry, I have not already defined it there. One can see that, one can actually, it is very easy to see that the derivations I am talking about, delta 1, delta 3 and r, the one parameter group generated by those derivations are actually given by this one parameter group. So we will use that notation. Okay, so and it has a sort of commutation relation, and if you use the commutation relation among these three, then one can show that you get this limit using that commutation relation to be this. You just don't take the expectation, expression with the second standard Brownian motion, you leave it aside, take the rest of the thing, and you have an alternative expression for that. With that expression, first of all, then once we have that expression, so what is the operator b phi e power tl acting on a vector f? Say f is in Schwarz class function in two variable t. Then this is the star product that I had introduced in the beginning, and this is one. This is just formal calculation. One can show that this is given by expectation of this integral, and after a change of variable, this integral is actually this thing. So this operator is actually what it turns out that it is actually an integral operator acting on L2 R2 with the kernel. The kernel is given by this expression, and it can be shown that this is actually a trace class operator for all positive t, and the kernel is continuous in each of the four variables. Once we have that, then we can actually compute the trace. The trace will be given by the integration along the diagonals. You replace T1 S1 by Ts and integrate along the diagonal. Then actually this is the expression of the trace, that one can show that for a sufficiently small interval t, there is some little technicality, like it won't be true for all t in sufficiently small interval. If you fix a subsequence in a sufficiently small interval of 0 going from right, then the trace actually looks like this expression. So it is given by to integral dt ds, and then you have to take some expectation. So once you have this, then you use this lemma. It tells you that here you can see that these expressions 0 to t e power 2 omega to tau d tau, this actually depends on the random variable omega 2. So this expression a plus minus actually depends on the random variable omega 2, and t, it can be shown that this random variable actually behaves like that. Along a subsequence, these two random variables actually goes to 1 pointwise almost everywhere. That one can show the lemma. And also, if you see, look at the expressions, like this is another, these two are another two random variables, and this is another random variables. One can study the behavior of these random variables for small t, and using these lemmas, the behavior of these random variables, one can show that this trace is given by this complicated looking integral. And actually we have the following theorem, that for every delta and for every phi, this limit t power half plus delta trace of b phi tl is actually 0 for every phi. So what we, by analogy of the classical thing or even the Euclidean Weyl algebra on plane, what we see that the dimension actually already drops here. Classically for the two-dimensional Weyl thing, what we had that if you take limit t goes to 0 plus t trace of this thing, this is actually given by the volume integral of phi. That's how we get the dimension to be 2 times 1 by 2, and at the same time we get the volume form. But here we already see that for every phi, if you take the power of t, exponent of t to be half plus delta, it is 0. So the dimension is definitely less than equal to 2 times this, that is 1. It is definitely, less than equal to 2. Actually, what we can show that, I will not go to the details of the how we prove the theorem, but we can show that there is a phi, however, that this limit actually, if we take the exponent of t to be half, is actually non-zero. So now, if you take this as your definition of dimension of the non-commutative space, like you have R in R, so that this limit is actually 0 for all phi, and you take the definition of the dimension to be the infimum of that set. First of all, you have to show that infimum exists, that we have already shown, and these things are contained in these two theorems actually, and the infimum is actually turns out to be half, and hence the dimension of that non-commutative Weyl plane, subplane sort of, that gets actually dropped. Previously it was 2 in previous calculations, but here we get is that due to the non-commutativity of the algebra itself and the presence of that non-canonical derivation, this dimension is actually dropping. That is the observation so far we have made. We don't know what is the significance or what can you say more about that. This is roughly the comment. And also we do not have any volume form, like in classical Weyl plane we had volume form, like this integral had a closed expression, like limit t goes to 0 plus t trace b phi e power tl, that had a closed form, like it is given by integral of phi with phi u v du dv, so that we had the volume form, a closed form. Here we have not been able to get any closed form, so we don't have a really volume form in the strict sense, but some limiting sense of volume form. Whatever the non-zero limit is, you can take it to be volume form, but unless we have some closed form, like it given by some integral of phi or whatever, then we really don't have the volume form yet. Thank you.
Okay, thank you very much.